all three of those things, or all four of those things, and then add them up. So the rotational inertia of the shaft, it's acting like a solid cylinder that's rotating about its central axis. So that's 1/2 mass of the shaft times the radius of the shaft squared. So, and I think it's important that more than one person calculate this, just in case there's like a calculator miskey. So 0.3933 kilograms times the radius of the shaft, which is 0.006375. And that's squared. And that's going to be something kilogram meters squared. Those are the units for rotational inertia. Okay, then we have I of the threaded rod. I'm abbreviating it. Now, this is an arcane one. When you have a rod that you are rotating about its center of mass along an axis perpendicular to the rod, it's 1/12 the mass of the rod times the length of the rod squared. So that was why we needed the length of the rod. So we have 1/12 times 0.0625 times, what was it, 0.343 meters and that's going to be something kilogram meters squared. I hope some of you are working on these calculations. And I of the 100-gram masses, or the 0.1 kilogram masses, we've got 2 of them, and the mass is 0.1 kilograms. It's just mr squared, okay? So 0.1 kilograms times 0.163 meters, quantity squared. Oh, shoot, I'm sorry. So it's 2 times m r, or I'm going to call it d, d squared. So this is d. All right. md squared, that would be the rotational inertia for one of those 100-gram masses. But we've got 2 of them, that's why I'm multiplying by 2. Okay, kilogram meters squared. And then we have the wing nuts. And that's just mr squared, or md squared. So it's the mass of all 4 of them together, 0.0227. Times that same distance, 0.163 meters squared. Hey, Miles, how's my time?
14 minutes.
Okay, left or into it?
Into it.
Okay. So, does anybody have any numbers?
7.992 times 10 to the negative 6 for the first one.
7.992? I'm sorry about that scene. 7.992 times 10 to the negative 6. Now, kilogram meters squared. Did anybody else get that? Do we have some core? Okay. And the reason I ask is because I think last semester I took somebody's word for the total rotational inertia, but it was wrong. So it's just good to check. Yeah.
I got 3.14 times the negative times to the negative 6.
For the first one,
Yes.
3.14.
I could be wrong. I don't know.
Yeah, I'm actually, when I did this yesterday, I got 8.196. I mean, I had a slightly different set of values, but try it again. Check your calculations. I'm inclined to go with this one. Okay, an I for the threaded rod. Anybody?
6.13 times 10 to the negative 4.
Yep. 6.13 times 10 to the negative 4th kilogram meters squared. And the 100-gram masses. Let's see, my numbers were a little different, so I can't tell you what. I got something like 0.0055 or something.
5.3 times 10 to the negative third.
5.3 times 10 to the negative 3rd. Okay. And the wing nuts, that's something times 10 to the negative 6, or no, it's times 10 to the negative 4 also. 6.03. Almost like Avogadro's number, times 10 to the negative 4, right?
Yeah.
Okay, so you've got that table filled in. Don't forget to put the units, because there aren't units in the table. There's like a parentheses for you to put the units in. So, I mean, it's a no-brainer. Just don't forget to put them in there. All right, now here's the deal. You're going to measure the time with the stopwatch. I'm going to say do 2 trials for each descending mass and then take the average. If they're really far apart, then do a 3rd trial and take the 2 that are closest together. You with me on that? You don't have to do 3 trials, just do 2. And then you're going to get an average time. So for each mass, this is the hanging mass, okay? It's not, we've got a lot of masses in here in this experiment, but this is the mass of whatever is hanging from the string. And so like your first one's going to be 0.050, and it's kilograms. Then I'm just going to go right to average time here. T average in seconds. Let's say for the first one you get 24 seconds. Okay? What's the next thing? The next thing is the linear acceleration. Okay, I'm erasing that. Oh, got that. So the linear acceleration in meters per second squared, or meters per second, there's a formula for that. I'm going to tell you what it is. It's twice the height divided by the average time squared. And I'm going to tell you where that comes from. It just comes from the old-fashioned kinematics that we did in January, where we had x equals x0 plus v0t plus 1/2 a t squared. So check it out.